Mark, I had one question. I will start with the question.
Yeah, so already to start.
Yeah.
So you have a question?
Yes.
Good.
Take the example of sorting with the Delauney triangulation. The nice thing there is that the conflict lists are disjoint. At any point of time, look at the conflict list. Any object participates in only one of the conflict lists. So for me, then intuitively it kind of makes sense. The generic, the bounds that you have. Bounds that you have, the two lemmas, stating that. But then if I look at, let's say, convex hull, if you look at a set of edges which are active right now, a single point can be part of many conflicts. So why is that not an issue? And it happens that there's a big bunch of points which are part of many conflicts all the time.
Okay, so maybe first of all, even for the Delauney triangulations, as we will see, the conflict lists are not disjoint because it's not just the points inside triangles, but inside the circumcircles. But okay, I guess from a very high level intuitive point of view, if you have many points that are present in many conflict lists, then these configurations are likely to be killed very soon because one of the points will leave.
Yeah,
Okay, but let's continue. So today I hope to at least do Voronoi diagram of the Delauney triangulation, talk a little bit about it. I think most of you are probably rather familiar with it. So who has never seen the Delauney triangulations or Voronoi diagrams? No one? So okay. So I will still go over it. I will probably go a bit quick because most people have seen it. I will point to the few important things that you need to remember for what comes after. And then I definitely also want to do the Schinzel sequences, and we will get to here, but we'll see what happens. Okay, so even though all of you have seen Voronoi diagrams and Delauney triangulations for most of you, let me give a small introduction, the one that I usually like to do, because I guess, or for me at least, it's a bit surprising and it's very nice because it shows that structures that seem very unrelated in geometry are sometimes actually very related. So suppose we want to have a 3D reconstruction of, let's say, a mountain area. 3D, there also seems to be lots of buildings. So what you can do is you have this plane, it's flying over this area. It's using what is called LiDAR technology to sort of measure points on the terrain. And so I have the surface, I measure a point. That means now I get, for a certain point, I get its elevation. So I get this point cloud of elevations, and then I want to make a continuous terrain out of it. Okay, so let's park that problem and look at something completely different, or so it seems. So I guess all of you recognize the guy on the left because his name is written in the middle, Descartes, who many years ago, centuries ago, wrote this book, Principia Philosophiae, and this picture features in the book. Does anyone know what it's supposed to represent, the picture? So it's supposed to represent charges. It is a map of the sky. So here, this is supposed to be the sun. These points here are planets that revolve around the sun, and these are maybe other stars. Okay, and this was his interpretation. Although I must admit I never read the book, so it might be that I'm completely off. That okay, this region here is sort of the influence region of the sun. And this is the influence region of that star. And so intuitively, maybe these planets are in the influence region. They revolve around the sun because that is their nearest star. Okay, in practice, of course, it has to do with the mass of these things and so on. But this picture suggests that it's something like this. So here you see what these regions are, and this is a Voronoi diagram. Right, all the points here are closest, the points for which this is the closest star. Okay, nice picture. This was I think Ukrainian mathematician, Ukrainian Russian from well, you see his birth that dates. Okay, so what does this have to do with the previous problem? Well, so what we had when we did the terrain reconstruction, we had this point cloud. So here this is the sort of XY projection of the point cloud. And for every point, we've measured the elevation, right? So we have something like this. Here at these points, we know exactly what the elevation is, but in between, we don't know. And we like to have a continuous surface, so we somehow have to also decide what is the elevation sort of in between these 2 points. So some kind of calculation maybe. So one thing you could think of is, okay, if I have this point here, it's very close to this one, so probably its elevation is kind of the same. So what you could do is, okay, let's take a Voronoi diagram, and then everybody here, this is the closest sample point, so let's give it the same elevation. Okay, is this nice? Yeah, it's not nice, right? Because it's not continuous. So you would get something like this, which doesn't make much sense. So instead, you want to have a continuous surface, so you want to interpolate. So what you want to do, maybe if these are my sample points, and here I should not say, okay, this is the closest, so it's the same elevation as this, but it's sort of maybe some weighted average of these 3 points. So what you can do is you compute a triangulation whose vertices are the sample points, and then you simply determine the elevation of the points inside the triangle using interpolation of the elevations of the 3 vertices. So that means that essentially each point is sort of lifted to its correct elevation, and then the whole triangulation is lifted. And you get a nice and continuous surface. But then this is what actually is often done in GIS systems or things like that. But now the question is, which triangulation? Okay, there are many different triangulations, exponentially many actually. And we have to pick one that gives a nice triangulation. But of course, in some sense, we don't know what the actual underlying elevations are, so it's maybe not even clear what is the optimal triangulation. And you can define it with respect to the surface, but you don't know the surface. So one way of doing it is to say the following. Well, if I compare these two, then this one looks a lot nicer. Right? Because, for instance, the elevation here of this point is interpolated between these 3 points, but this point is quite far away. And here, exactly the same point is interpolated between, well, the same 2 vertices, but also this one, and this is much closer than this one. So somehow, if you have very long and thin triangles, that seems bad, because then you're interpolating with points that are far away. So maybe what you want to do is you want to avoid these long and thin triangles. And let's try to turn that into some optimization problem. So let's try to make sure that we avoid thin triangles. So over all possible triangulations, let's try to find the one whose smallest angle is as large as possible. Okay, so let's compute a triangulation that maximizes the minimum angle. And that's, okay, that seems difficult. We have exponentially many triangulations, so how do we do that? But I guess, as most of you know, it actually is closely related to Voronoi diagrams. Right, so if I take the Voronoi diagram I have here, connect any 2 points when the cells are neighbors. Okay, these are also neighbors. Now, first of all, if the point set is not in degenerate position, so there are no 4 co-circular points, for instance, then this is a triangulation, which is maybe the same as saying that in the Voronoi diagram, all the vertices have degree 3. And secondly, this is the triangulation that maximizes this minimum angle. Okay, so that's quite nice. So that means that if we could compute the Voronoi diagram, for instance, we can always also compute this triangulation that maximizes the minimum angle, which is called the Delauney triangulation. And there's some other Russian mathematician here. Okay, so that's nice, and I guess all of you probably know that. The important property that we'll also be using in the algorithm is the following. If you look at a triangle in the Delauney triangulation, and like this one, I take the circle that contains the 3 vertices of the triangle, then there are no other points inside. Okay, and this is if and only if. So we want to compute all triangles whose circumcircles are empty. So here, this triangle is not part of the Delauney triangulation because I have this diagonal, and indeed, its circle, there's another point inside. So, okay, there's an obvious algorithm that would say check every triple. For every triple, take the circle, check if there's a point inside. That would run in n to the power 4. But yeah, you can also do it in Hamilton, as if you took Rahul's course, you probably know how to do it. There are different ways for if you want to compute the Voronoi diagram, and then you can take from that, get the Delauney triangulation, you can do a plane sweep, you can do divide and conquer. If instead you want to directly compute the Delauney triangulation, then you can do, for instance, randomized incremental construction. So let's have a quick look. And yeah, let me go through it rather quickly perhaps, but it's maybe good to do it to see if we still remember the framework that we looked at last time. Okay, and yeah, what we need is that if you look at the Delauney triangulation, the number of triangles is linear, which is, I mean, it's a planar graph with a linear number of with n vertices. So clearly, all the faces and the number of edges, and so that's all linear. So that's nice. This was the framework. Right? We have input objects, and then we have to define configurations that need a defining set, a conflict list, and the goal is to eventually compute all configurations where the conflict list is empty. Okay, and we will do that incrementally. So the input objects, well, they're obviously the points. What are the configurations? Oh, let's do the triangles. So each triple of points determines a triangle. So n cubed number of configurations. And indeed, they're defined by a constant number of points, constant number of objects. But that's nice. So what is the conflict list of a triangle? Yeah, so it's not just the points inside the triangle itself, but a triangle was present if and only if there are no other points in the circle to the triangle. So the conflict lists are all points inside that circle. Okay, so here the conflict list of this triangle would be these 2 points. And then indeed we, what we want to compute, which are the configurations that are not in conflict with anything, those are exactly the triangles of the Delauney triangulation. And so, yeah, we can now do what we did before. We start with a random permutation. We initialize. Initialization is a bit more tricky here. And then after initialization, okay, I'm adding one by one all the points, remove the configuration, so the triangles that are in conflict with a new point, create a new triangles, and so on. So here, box, or maybe a big triangle, and that should be sort of the points of the triangle or the points of the bounding box should be far enough away so that they don't influence what is going on here, or you sort of try to artificially enforce that by saying something like, oh, by definition, whenever you're checking whether that point inside a disk, the answer should be no, something like that. Okay, so let's see, we start with a big triangle, and now the algorithm is quite simple. Yeah.
Why can't we just start with the first 3 points and the triangle as our initialization?
Okay. When we go through the algorithm, what we typically do is we're going to find the triangles, I mean, the point containing the triangle and work from there. But now it can be outside, and that's a bit awkward. That's why it's easiest to do it like this. So, okay, maybe this is my first point. I notice that it's inside the circle of this big triangle. So that triangle disappears, and I get 3 new triangles. Okay, I maybe insert the next point. Which 2 triangles disappear? Well, here it's in the circle, so that one disappears. It's also in the circle, this one, so that one disappears. It's not in this circle, so this is it. It's all inside this one. Okay, and the new edges always go from the most recent point to, we've removed some of the triangles. That creates a hole in the triangulation, and you always add points, edges from that new point to the vertex of the hole. Is it clear to everybody why it can never be that I get a new edge for which the new point is not one of its endpoints? To answer that, maybe you need another fact which I didn't tell you, which is, okay, a triangle is present if and only if its circumcircle is empty. An edge is present if and only if I can draw some circle, right? There are many circles through these 2 points, but I can find some circle that is empty. Okay. And that means, of course, that if an edge is present when this point is there, okay, that means that I can somehow find a circle through these 2 points of that edge that doesn't contain any other point, then obviously that circle is also empty before this point was present. And so that edge must have been already there. So the only new edges, they all must be incidents to this new point. Okay, so I get it. So after creating those things, I need to create a new conflict list. Okay, let me not go into that, but that's the sort of most time-consuming step, and that's maybe also sometimes where if you implement or if you want to apply this framework, this is probably where you're going to spend most of your time thinking, how should I do it for my particular case? Okay, and then we have this lemma. So this was saying that the number of new, in this case, triangles, new configurations that appear, so the ones that are in after step J that are present there but were not present before, the expected number is this. So what is it at this point? For this example, well, this thing here, it's the expected size of the Delauney triangulation of a subset of J of the points. Okay, so instead of expected size, let me simply take worst case size, because here the worst case, it's linear, right? Because it was a planar graph. So this is order J. Okay, so this is constant. Okay. Which, again, using backwards analysis, we can see, because if I have my triangulation, Delauney triangulation, after adding my J points, now I remove a random point. Which triangles disappear? Well, exactly the one for which this is one of the vertices. So the number of triangles that disappear is the same as the degree of this vertex. Okay, I have a planar graph. So the total degree is linear. So if I remove a random point, then its expected degree is constant. So, okay, this makes sense. This is more complicated, but you can see again, if we could do all this updating in time that is linear in the overall size of the conflict lists of the triangles that disappear, then this we know that this is J, then I get here n over J, and it sums to n. Okay, so this is did you cover this algorithm in the course, or maybe the one with the history graph, maybe?
Randomized. Randomized.
But with conflict lists or with? Okay, so you can also do it instead of maintaining these conflict lists. Remember that there was other version where you maintain the whole history. So in this case, you would maintain a directed acyclic graph whose nodes correspond to triangles that appear at some point. Or if this directed acyclic graph, the leaves are the triangles of my current Delauney triangulation. When I add a new point, I search. Okay, then I can do it in two ways. One is you could search and then immediately find all the triangles that you're in conflict with, but then it's not a single search path, but you have to branch, because now you would go to a triangle if you're in its certain circle and they can overlap. The alternative is you only find the triangle that contains it, and then you start flipping edges until you get the right triangulation, and then you get new triangles and you update it or only this history graph and so on. Okay, but
it's always equivalently conflict graph and conflict list and
the history graph.
Yeah.
Essentially, yes.
Any pros and cons when you want to apply each one or?
I think in terms of storage, the history graph might sometimes be, so for storage, it makes a difference. Right, the storage of the history graph is never more than the sum of this. While for the conflict list, okay, you explicitly have all this, so that could be a little bit more.
Still, it's a data structure.
Yeah, so the other thing is, you immediately get, like also here, if you have this, the history graph, you immediately get point location data structure on the Delauney triangulation. Okay, the question is, it's not trivial or it's not easy to analyze what is actually the worst case query time for an arbitrary query point that has nothing to do with your input points. But at least you immediately get this this structure, which is nice, maybe. Okay, so this we have seen. Yeah.
It's the Delauney triangulation in expected linear time. So this is expected order log in time, but
No, that's not possible.
worst case is not possible, but even expected linear time is also.
Unless maybe you assume some distributional point set,
Oh.
but without that, I mean, also sorting in expected linear time is not possible, depending on the model of computation, perhaps. Okay, a few nice facts. I don't know if any of you heard of the concept dilation or stretch factor of a graph. So it's defined as follows. Let's say I have a set of points. You can also define it in a more abstract setting for a, say, edge-weighted graph. I have a set of points, and now I wonder how well do the shortest paths in these in this triangulation, how well do they approximate sort of the actual distance between 2 points? Right. So ideally, perhaps if you have a set of points, you would like to have a direct connection to everybody else. Right. Suppose this is a road network. Okay, if you go from Bangalore to Mysore, you would prefer to have a road that goes directly there, but maybe you have to go through some other cities and you have a slight detour, but you want this detour to be small. So the stretch factor is if I take any 2 points and I look at the length of the shortest path in the graph divided by the actual shortest path. So that's sort of the detour. You have to maybe drive 30% more. Now you take the maximum over all possible pairs of points. That's the dilation of this graph. And the Delauney triangulation has a constant dilation. Actually, it's slightly below 2. And if you want to work on a nice but very difficult open problem, you can try to see if you can prove a better bound. It's known that it was conjectured that it should be pi over 2. That turns out to be false. There's a construction where the stretch factor is slightly larger than pi over 2. But there's still a significant gap between this and this roughly pi over 2. There are also other graphs that have a better stretch factor. So actually, for any epsilon greater than 0, you can compute some kind of graph with where the stretch factor is only 1 plus epsilon, and the number of edges is, for fixed epsilon, still linear. So the number of edges is n divided by epsilon. That means stretch factor 1. Okay, there's only one way to get it. Take the complete graph, so you need n squared edges. But as soon as you want stretch factor 1.1, you're happy with that, you can do it with linear number of edges, order n. Okay, this, I don't know if you showed this in the course, but that if you look at a Voronoi diagram in d dimensions, it's essentially the same or roughly as half space intersection in one dimension higher. So here's an illustration if you go from 1D to 2D. So here I have a set of points in 1D. Its Voronoi diagram, okay, the Voronoi set of this point is from minus infinity to here. This is midway between these 2 points. The Voronoi cell of this guy is from here to midway between these 2 points. Okay, now if you do the following, you take the parabola x squared. Each point I project onto this parabola. At the point where it touches, where the projection is, I take this tangent. Okay, so here I also took the tangent, and here I took the tangent. Now I take, for each of these tangents, I take the half plane above that line. I take their intersection. That's this blue region. I project, okay, this is a polygon, well, I'm bounded on one side with here a vertex and here a vertex. I project these vertices back onto the line. And I get exactly my Voronoi diagram. So in other words, if I look at this point, it has a line here. That line contributes an edge to this region here. If I project the edge, it's exactly the Voronoi cell. And that holds, always holds if you go from d dimensions to d plus 1 dimensions. So if you can compute the intersection of half spaces in d plus 1 dimension, you can also compute Voronoi diagrams in d dimensions, and then also Delauney triangulations in d dimensions.
So in d plus 1 dimension, what is like that is y equal to what? In this case, x square. D plus 1 dimension.
So you take z equals x squared plus y squared.
Can you contingent on the fact that we are looking at Euclidean distance?
Yes.
So similar, is it interesting to also look at these stretch factors and for other metrics or bounds?
For the, okay, something like this, I haven't seen there, but for these stretch factors, or those graphs are called spanners.
Yeah.
Okay, people look at even spanners of arbitrary metric spaces and things like that. Where the bounds, you cannot get the same bound. So for Euclidean space, you can get a 1 plus epsilon spanner with a linear number of edges, I mean, depending on epsilon. In arbitrary metric spaces, this is not possible. If your metric space has bounded doubling dimension, then you can do it, and so on. Okay, this one, I guess everybody knows how to do that. You have to use duality. Right, so if I have, you have this duality transform that if you have a line here, line y equals ax plus b, you can map it to a point, let's say a minus b here. And if you have points here, you can map them to lines here and so on. This goes back and forth. And then essentially, if you look at the intersection of these upper half planes here, that corresponds to the lower convex hull in the dual space. And if you want to have the whole convex hull, okay, you should do this, but then you should also look at the things below the lines and take the intersection of these lower half spaces, and then you can combine the two. Okay, one maybe interesting other application of Voronoi diagrams is in some frequency assignment problem, namely conflict-free colorings. Anybody has seen conflict-free colorings before? Except for Raoul, who has seen everything that I'm talking about probably.
Coloring graph. Intersection is defined.
Yeah, so you can also define that on hypergraphs or, but okay, so here the motivation that people use to come up with this problem is the following. Suppose I have a set of the centers of these disks are transmitters, let's say cell towers or towers for cell phones. Okay, they use a certain frequency to communicate with people that are using that cell tower. Okay. And now the idea is that okay, you need lots of these towers, but if, for instance, so if I'm here with my phone, I can communicate with this cell tower and with this one. If they would use the same frequency, that's maybe an issue because then you get interference. So if I'm here, I want to make sure that, okay, these two frequencies are not the same. If I'm here, okay, it's fine if these two frequencies are the same, as long as this one is different. Because then I could decide to use this cell tower. I don't have any interference because it has a unique frequency. And the other ones, they interfere, I don't care. So what you want is the following, and now I'm turning frequencies into colors, right? So different frequencies are different colors. So if I have a point Q anywhere, right? So that's me with my cell phone, then define dq to be the set of disks that contain that point. Right? So those correspond to the cell towers I could potentially use. I want that this set dq, if I look at all the colors, there's at least one disk that has a unique color among that set. Right? Because then I can use that one for my phone call. So I want to color the disks such that whenever you are somewhere in the union of these disks, but if you're outside, you don't have connection, there's nothing you can do. But whenever you're in the union of those disks, there's one disk among the ones that contain that point that has a unique color. And now you want to give out as few frequencies as possible, but to use as few colors as possible.
What is XQ? XQ. So for any Q.
Okay, so that is DQ. Yeah. So this thing should be DQ.
These three disks on the left must have distinct colors.
For instance, these must all have distinct colors because as soon as you give any two the same color, like these two, okay, then a point here has a problem. If these two have the same color, then points here have a problem. So this, for instance, is a valid coloring, I hope. So indeed, they have all distinct colors. This one, okay, it's easy. And here, whenever you're in here, you can use the green disk. When I'm in here, I can use blue. So these have the same colors, but that's okay. These have the same colors because whenever I would be in the overlap of these two yellow guys, I can take the green one. So now the question is, if you have n points, how many colors do you need in the worst case? And disks. Any guesses? I guess. any guess would purely be like something like, oh, square root of n is a nice function, or log n is nice, or
It was 3, then n equals 3. You do.
yeah. So you could also think, oh, maybe it's n. But because if I now put all of them somehow on top of each other in a complicated fashion, okay, we'll see.
It has been how many intersections, like one common intersection, like everybody intersecting, and how many ways that can be done. For example, that is I1 intersection, I2 intersection, I2. And that is why the lecture needs 3 colors.
Yeah.
But that would not be the case for arbitrary large.
Yeah, so maybe intuitively, you could say something like, okay, if any possible subset, for any possible subset of disks, there would be a point that contains exactly that subset and nothing else. Okay, that happens for these 3. Then you're probably in trouble. But that, I hope you realize, can never happen, because the number of subsets is 2 to the n, but the total number of regions is at most n squared, right? You have at most n squared intersection points in this whole collection of disks. So the number of, if you look at this as a graph where the intersection points are the nodes, okay, and these are the regions, I could have n squared nodes, so not more than n squared regions. So there is hope, and indeed it turns out that we can do a lot better than n, namely log n. And let me describe how to do it. So first of all, I'm going to invert the problem. What I was saying before is I give you the disks, and you have to color the disks so that for a point, well, it has a disk with a unique color. Now, and I'm going to, for simplicity perhaps. So here, all these things were disks that, okay, where there was the range of some cell tower. And I assume that all the cell towers are equivalent, so all these disks have exactly the same size. Okay, so now I have unit disks. So that means that I can replace all the disks by their centers. So here the disks become points. And I replace the point here by a disk, by a unit disk. Right, then obviously this point is contained in a disk here, if and only if the corresponding point to that disk is contained in this disk. So now I'm going to color the points such that for any possible unit disk and actually any possible disk of any radius, I have this property that I've at least one of the points has a unique color. And maybe you could already think that, well, I have points, I have disks, maybe something with Delauney triangulation because you have empty disks property, and indeed that's what we're going to do. So it's a very simple algorithm. Here are my points that I want to color. I compute the Delauney triangulation. And remember that PQ is an edge if and only if there exists a circle that goes exactly through those 2 points, actually, that is otherwise empty. Okay. So that's an important property. So now I compute the Delauney triangulation. I take an independent set. Okay, this is hopefully an independent set. I give everybody in the independent set the same color number 1. And then I delete those points, or I ignore them, and I repeat. Right, I take the Delauney triangulation of the remaining points, compute an independent set, give it color number 2, green, and repeat. Here, independent set, and so on.
Maximum independence.
And I want to have a large independent set, so that the number of iterations is small. And now we're not concerned maybe with the how much time it takes to compute. So the question is, how large can we always pick this independent set? Yeah, I mean, the Delauney triangulation is a planar graph, so with a 4-color theorem, you can color it with 4 colors. That coloring is a different coloring. So if you take the largest color class, that's at least a quarter of the points. Okay, so that means that the number of colors is logarithmic, right? Because we have color 1, but the number of colors, let's say C of n is 1 for the independent set, plus C of 3/4 n, because I removed 1/4 of the points. Okay, so that solves to log n. So why is it conflict free? So what I have to prove is that okay, this was what we had. What we have to prove is that any disk, if it contains at least 1 point, then one of the points has a unique color. Okay. So let's do some case analysis. I look at the disk. If I'm lucky, it has 1 point with color 1. Okay, that's that. If you don't have any points with color 1, okay, then either okay, there's still some points in there, right? Because you assume that we have at least 1 point. And now I simply say, okay, these points were colored inductively. So with my induction hypothesis, I can assume that from the colors 2 to whatever maximum number of colors I use, that I have one with unique, there's a unique point. Okay, so the difficulty is if you have, like here, at least 2 points of color 1, right? 0 points of color 1 induction, 1 point of color 1 done, 2 or more points of color 1. Okay, what happens now? I claim that it cannot be that the points of color 1, that those are the only points inside the disk. Okay. If that my claim is true, and I do have at least 1 other point, then I can apply my induction again. There must be at least 1 other point. Yes. So if there are no points in there, there may be lots of blue points. I can sort of take that disk and start shrinking until I have only 2 blue points left inside. And they are on the boundary. But then there should be an edge between them in the Delauney triangulation. And they would not be in an independent set. Okay, so yeah, that finishes the proof. Is nice. So there's also a lower bound of log n, which is not very difficult. There are not much open problems here, no. So even if our point set is simply this. You cannot do better than log n. So this is my point set. My disks, the important observation is that for any consecutive subsequence, I can draw a disk that only captures these points. Right, so that means that for any subsequence, there should be a point with unique color. Okay. So why does this lead to log n? Well, first of all, there must be a color that appears only once. Because otherwise, if all the colors appear at least twice, then this disk doesn't have anything with a unique color. Okay. So there must somewhere be, let's say, this guy. It must be the only red point, say. So now, what is the number of colors I need? Well, I mean, here and here, colors that I use here, I can also use here without any issue, because whenever you have a disk spanning things on both sides, the red point will be the one. But if I look at this part, just that part, okay, I essentially reversely, I have the same problem. Same thing on this side. One of them has at least n/2 points. So you get all.
Is it easy to show a two stressing factor for Delauney? Not two methods of self.
I don't know. Is that easy? I don't think it's necessarily easy, but I don't know. Easy for maybe for you it is, but I think for me it is not. But I don't remember. I never really thought about it much. Question about snacks. Are there any?
Yeah. Okay.
Okay, then I think this is an excellent time for snacks. Unless are there any other questions?
I think like these equitable coloring is considered that you want the number of vertices same color to be like balanced. And these problems that are studied.
Foreign problems that have been studied, including something along the lines that you mentioned, but that's quite different from these types of coloring. So here, if you want to have a nice open problem for colorings, so what we did now is we said, given a set of points, color them such that the coloring is conflict-free with respect to disks. Right, for any possible disk, if it contains at least one point, there's also a point of unique color. As far as I know, I mean, you can do that also. Let's color with respect to your favorite object. So coloring with respect to rectangles, I think there are no tight bounds known, and it's not polynomial, it's n to the 0.2 something, I don't know. But yeah, and I don't know, do you remember how big the gap is, what is currently known? Yeah, so, yeah.
Square similar bound should be known. You can take L1 ball of squares.
For squares, you should be able to do exactly the same thing, but in the infinity metric or.
I think this is more like a technical curiosity than But like, are there more general definitions? Like, if for every point where two or more intersect, then you need to have two unique, not just one.
There are also things like that, as in, you could think, if you think about the application, sort of a fault tolerant setting where maybe if one of your cell towers fails, you still want to have a unique frequency and then so on. Yeah. Okay, snack time.
What I see in that Delauney graph, this instance looking at this particular, it what I see Delauney graph looking like.
There's no internalization. Okay, so here it's not quite well defined. I mean, if they're really on a straight line.
Yeah.
Okay, there's no triangulation essentially.
No.
Look like an off-road.
I guess that I would define maybe the triangulation to be of all these edges. So first of all, if you have, even if they're not all on a line, as soon as you have 4 points on a circle,
Yeah.
and that circle is empty,
Yeah.
then we should talk about the Delauney triangulation, about the Delauney graph, which would now not have triangles, but it has a quadrilateral. Interestingly, then, so you can triangulate it in different ways. You get different Delauney triangulations. No matter how you triangulate the points, if they're all on a circle, the smallest angle is always the same. So here, I would say that if the points are all on a line, we would have a Delauney graph, which would have all these individual edges and maybe one big edge going back or something like that.
Maybe the Voronoi diagram is going to be these vertical lines. You connect to the Voronoi.
Yeah,
This one,
yeah.
it is
So
the path.
in that sense, it would just be a path. But indeed, if you want to do some kind of lateral path, it will not be.
It's not like, but it's the graphs, you know, to belong to the maybe. Are they known to belong to classes, like, it's a planar graph, but beyond that.
What are next year? One of the third department. Yeah, understanding it, you are for the English. What is I assume that. It's also a spoon better. I just said that we can be one here. Yeah, I'm not aware of it. I'm it's also different. Even the theory so then everybody wants to come out of this. That's why you want to take a talk. The thoughts. Thoughts of yes, sir. I thought we should practice very This time we don't know this. Not I.
Oh,
No.
So I like these samosas. I think they're better than the ones at Southern.
Okay. Yeah, these. Yeah. No, but you have them for lunch or?
I have them for lunch.
For lunch, you have a samosa.
That samosa and the
That's
fruit salad.
compensating.
Weird combination, like fruit salad and samosa.
Yeah, wait. Even inside samosa, I'm just heard.
Samosa factory there, what the, yeah, the bucket.
Different types of coffee. Yeah. But inside actually beat yourself. But Instagram, because it's very creative in the digital, they want to show.
Okay.
So what's I say? Hi.
Yeah. Or really, some of our fruit salad.
Okay, everybody back? At least the ones who are here, yes. Okay, so who already saw Davenport Schinzel sequences?
I wrote a book on, so read some parts of.
Okay, yeah, so these are Mr. Davenport and Schinzel. And they wrote some paper that had something to do with differential equations, but one of the things that came up was this combinatorial question. So look at a sequence of the numbers 1 to n, right? So 1, 5, 3, 7, 3, 7, 5. So you're only allowed to use n numbers. And there are two rules. You're not allowed to put the same number twice in a row. And, okay, there's a parameter S. And you're not allowed to have this, something like this as a subsequence. Right, so depending on the parameter S, you're not allowed to have some I and then at some later point a J and then the same I again and then the same J again. And then in total S plus 2 times. And then the question is, how long can this sequence be? Okay, so
you say this is not allowed, mean that there shouldn't be a subsequence which is like ij s plus 2 times.
exactly, yeah. So let's look at a more concrete example. So let's say that n is 9, so I'm allowed to use the numbers 1 to 9, and s equals 2. Okay, so I'm not allowed, so this is now 4, so this would not be allowed. Okay, so of these things, for instance, the first one is not allowed because I wrote the number 2 twice in a row. Okay, this one is also not allowed because I have 2 and then a 1 and then a 2 and then a 1 again. Okay, the other one, if I did not make a mistake, it doesn't violate my rules. Right, I definitely did not put the same number twice in a row, and there's never like 6, 4, okay, there's no 6 again. You can check. Okay, so how long can this be? Okay, obviously it's going to depend on n. It's a function of n, but also a function of s. So exercise, let's try to solve the exercise together. What is the maximum length for different values of s, small values as a function of n? And let me write that as this function.
You can think that they are in the order S, that this length S plus 2 instead of S, like why they are different S and S plus 2.
We'll see perhaps why people wrote it like this.
So the thinking passage is good. Looking at just the sequence of size 1. It needs to be at least 2.
S is 0 doesn't make sense.
Okay.
But then it's.
But if it's equal to 1, then you can say S plus 1.
S is equal to 0 doesn't equal. S is 0, it's just 1.
But starting value of S is 0 or 1?
Okay, so let's try to do s equals 1. So what's the longest thing you can do? N. I mean, it's definitely allowed to simply write 1, 2, 3 all the way up to n. But I don't repeat anything. And now for s equals 1, I'm not allowed to have some I, some j, and then I again. But so that essentially means that you can never repeat a number. Right? Because as soon as I put a number, I cannot write the same number immediately again, because that violates rule 1. So I have to write something else. So I have some I, then I write something else, j. Okay, now I'm not allowed to use I anymore, because it would violate rule 2. Okay, so this is just n. S equals 2. Does anyone already have something longer than n? 2 n minus 1, how do you get it? Yeah, so 1, 2, 3 up to n, and then n minus 1, n minus 2, and so on. Okay, and you can verify, okay, you never write the same thing twice in a row, and there's you don't have this now s equals 2, so it's 4 things, and that doesn't happen. So anything even longer?
It's like the same number can't appear more than twice.
It can. I can do 1, 2, 1, 3, 1, 4, 1, 5.
G there has to be different from I. Like in condition 2, it's sort of.
Yeah. Yes. Or maybe proof for 2n plus minus 1.
What you said is also 12 minus 1, 1, 2, 1, 3.
No, I'm not saying that it's 2. I'm just saying that an individual system symbol, there could be symbols that appear more than twice. But then probably what I said actually also gives 2 in minus 1, right? I just have 1, 2, 1, 3, 1, 4, and that's all. Okay, let's try to prove that this is actually tight. So what I'm going to do is okay, so here I have my set of symbols, and I'm simply going to write them, sort of renumber them so that the first symbol is a 1, then the next symbol is a 2, and whenever I get a new symbol, I use the next number. Right, so that means that whenever a number, the ith number appear, I label it I. So that means that n, okay, I'm allowed to use numbers 1 to n. So if this n is here, then I've seen all the other numbers before. That's the way I've relabeled the numbering. Or in other words, n is simply the one whose occurrence is last. Okay, so first of all, you can see that n can never appear again. Okay. It cannot be immediately here, violate rule number 1. If it's later, okay, I have n, in this case 6, I have another n, but I knew that 6 is also here, because everybody appeared before n was the last one that appeared. So then I would have 6 and 6n, and that's not allowed. So n cannot appear again. So what I want to do, so n, this is the only time n appears, I delete it and I imply induction. N plus 1 is not, right? We only have n symbols, this is the other. So perhaps you would think that initially, okay, I delete this, I imply induction, so I get this, I put a 1 here, and that's it. But that's wrong. I mean, first of all, you can see it wrong, because if you put a 1 here, then it would solve to n, and we already have an example of 2n minus 1. So why is this wrong?
7 could have deletion would validate 1.
So if I delete this, then these, it might be that these two are the same. So that means that I also have to delete something else. And that's why I get the plus 2 there, and then I get exactly my number. So that's a 2, and then I get s equals 3. Any guesses?
Sorry, I didn't understand how deleting 2 will give you a valid. For 6, for example, we could again have 7. But aren't we actually deleting?
So, okay. The argument is maybe a little bit more. If there's 7 here, then there was also a 6 here, and then it would already violate. So that's not possible.
It's less than equal to, so like if there's a 7 after a 6, you can only delete one and that's it's fine. It's an upper bound which holds always.
Yeah, so, I mean, yeah, I mean, you can also say, okay, if these are different, okay, then just deleting n is fine. If they are the same, yeah, then you delete those two, whatever comes here, it now also comes back. S equals 3. Okay, so this is a super difficult problem. The bound is this, where I guess a number of you have seen this alpha n from union find. So it does grow faster than linear, but not much faster because this alpha n is growing slower than this. It's the inverse of this function here. So this function an that is defined like that. I think the sort of interesting thing is if you look at the values of this capital A, okay, so alpha n is the functional inverse. So this grows very quickly, this grows very slowly. This alpha n, okay, alpha of 1 is 2, of 2 is 4, so it starts kind of modestly, then goes to 16. And then I get a tower of 65,000 to the 2, 65,000 times. So this is a fairly large number. I think either this one or A5, maybe A5 is larger than the number of atoms in the universe or something like this. So this is growing super rapidly, so that means that this is growing super slowly. So for all practical purposes, it's still linear, but in theory, it grows slightly super linearly. And these are sort of the general bounds. So the important thing is that whatever your constant is you take any constant, then it's almost linear. Okay, for instance, it's smaller than n log star n. So log star is the number of times you have to take the log to get u log 1. And yeah, so there are more precise bounds known for S even is this, for S odd is that, and it's all very small. So the important thing is that it's almost linear, and these Davenport Schinzel sequences or these bounds, they show up in a number of geometric structures as sort of the complexity of the structure you can analyze using these Davenport Schinzel sequences, and then hopefully show that the geometric structure only has near linear complexity. So we'll do some examples of this.
I think like DSS is little over DSS plus 1 or S greater than.
I think, yes, all these bounds are slightly different. So I think the next one, so DS4 is n times 2 to the power alpha n. That sounds maybe bad, 2 to the power, but this alpha n grows so slowly that even 2 to the alpha n is much slower than log star. I forgot what 5 is, but indeed they're all, I think they're all different. There was something with even an odd, but okay. Let's go to arrangements. So from the first part of the course, we talked about randomized incremental construction, which is a powerful paradigm that you can use to construct many geometric structures. So now many algorithms and analyzing sort of certain parts or certain substructures in arrangements. That's what you quite often see. Hopefully on Friday I'll get to some applications of these things. But now let's have a look at the basics. And I want to start by some motion planning application. So let's say that I have this workspace in plane. I have some vacuum cleaner robot, which is my disk. And okay, typically the goal of a vacuum cleaner robot would be to vacuum clean the whole thing. But now I only want to go from here to here. So maybe this is sort of, okay, this is a weird place to put the charging station for the vacuum cleaner, but let's say it wants to go there because that's where the charging station is. Okay, this is, yeah. Okay, so how can you do this? A simple way of doing it is the following. So in case, because our robot is a nice disk, that means that it's not colliding with any of these obstacles, if and only if, let's say that the radius is 1, if it's the center is distance at least 1 from all of the obstacles. So for this obstacle, for instance, as long as the center is outside this shape, I'm fine. So I take all these shapes, these expanded obstacles, and now the question is, from this point here, is there a path simply that avoids all these expanded things that ends up at my target location? Okay, what can I do? I compute maybe a vertical decomposition, perhaps using randomized incremental construction. And then I look at the dual graph. So every node in the graph corresponds to one of these trapezoids. And then essentially what it boils down to is simply finding a path in this graph from this node to this node. Okay, so that's quite simple. And what you see here is that I have, now I'm drawing a partition the plane into different regions. So this is called an arrangement of, in this case, these curve things. And here I can go from here to here. For that, I would have to look at only the region containing that starting point, because that is the region that I can reach. Right, so I could, maybe when I do this vertical decomposition, I only have to do the vertical decomposition of sort of this, what is called the free space. I don't care about the vertical decomposition inside these obstacles. Right, and that could be good because maybe the total number of trapezoids I have in this free space, or sort of in this single region, could be much smaller than if I would also construct trapezoids inside. Okay, so this is the reason for maybe looking at, if I have this so-called arrangement of things, looking at only one cell and not the complete arrangement, not the complete decomposition of the plane. So then the question is, okay, I guess you will probably quickly come up with an example where you have let's say n obstacles, maybe the obstacles are just line segments, and I have a robot, And now I take this, I expand each of these obstacles. So my line segment, and I've another line segment. Okay, I create all these intersection points between these things, that if I have n line segments, I can create n squared intersection points. But if the line segments are very close together and drawing all these things, everybody intersects everybody else. But sort of outside of these regions, that's actually much smaller. In this case, these blobs are what are called pseudodisks. You can prove that for any pair of them, they can intersect in only 2 points. And you can use that to prove that actually this free space here only has linear complexity. We're going to look at a more general problem where I don't assume that these curves are generated in this way, but I just give you an arbitrary collection of line segments or curves. And now you ask, how complex can a single cell be? Okay, so maybe a bit of terminology. You've set of lines or segments or curves or anything you can think of. Let's think about it in 2D. Then the arrangement is the partitioning of the plane into, I have these regions, so-called faces. I have edges, which are parts, okay, or segments, parts of such a segment between 2 intersection points or between an intersection point and an endpoint. And I have vertices, which are either intersection points or endpoints of segments. And then for curves, you can do the same thing. And the complexity is always measured as the total number of these features. So
Not a simplistic form.
it's not a simple complex, no. So the complexity of this cell here would be, okay, I have 1 for the cell, and then I have to count the number of edges and the number of vertices and so on. So people looked at various different substructures in such an arrangement. Right? You can look at a whole arrangement. You can look at a single cell. Was inspired by these motion planning applications. You can look at what is called the upper envelope. On Friday, maybe we will see some applications of that. In other words, if, let's say, these things are X monotone curves or line segments, you can see this as a partially defined function. And so here's the x-axis, and the height is the value of the function. And then this is sort of taking the maximum over all these functions for every value of x. You can look at all the cells that are intersected by a specific line or by something else. That's called the zone. You can look at levels. So the K level would be, okay, you look at all the points on one of the lines that have exactly K other lines below them. So this would be the 1 level, because there's always here, there's 1 line below it, namely this one. So this is the 1 level. And for each of them, you can ask yourself, how complex can it be? So let's try to do this for a few simple examples. So if I look at the whole arrangement, so I have a collection of n simple curves, simple meaning a curve doesn't intersect itself. maybe instead of curves, I should write arcs. I mean, they can also, and it's not that they're necessarily infinite. And let's say that any pair of them intersects only constant number of times, say S times. And obviously, if you don't put a bound on that, then even for two curves, it can be arbitrarily complex. So I'm putting a bound on the number of intersections, say they're polynomials of some bounded degree. And then what is the complexity of the whole arrangement? So look at all the cells. Okay, that is pretty easy. Right? Because in the worst case, everybody intersects everybody. So every curve intersects every other curve in exactly S points. So, okay, the number of vertices is, okay. I have for the end, each curve has two endpoints. Then for each pair, I maybe have S intersection points. So S is a constant, so that's this. And then for the rest, okay, this thing now, if I put these intersection points, I can see this as a graph whose nodes are endpoints and intersection points. Because I put a node on every intersection, this graph is now planar. And therefore, okay, also the number of edges and the number of faces is linear in this number. Okay, and if you want to be more precise, you can use Euler's formula to do all these things. Okay, so this is easy and not so interesting. So now let's look at the upper envelope. And let's assume that my curves are X monotone, right? So they don't curve back, but every vertical line intersects the curve at most once. And actually, they're infinite. So going all the way from minus infinity to plus infinity. Then I claim that if I look at the maximum, so this upper envelope, as you can see here, function 2 appears, or curve 2 appears, and it appears again. It doesn't seem to appear once more. So maybe a single curve can appear many times, but I claim that overall, the maximum complexity is actually, okay, and the message is, it's almost linear. And it depends on how often they can intersect. So how would I prove this using Davenport Schinzel sequences?
Identifying the upper envelope curve that sequences.
So indeed, I do this, right? I label every edge here with the curve that generates it, by 1, 2, 3, 2, and so on. And I claim that this is apparently a Davenport Schinzel sequence of order S. So there are two conditions, right? One is you should never put a symbol twice in a row, well, that's sort of by construction. The other is we should check that you cannot have I and some later point j, and then I again, and then j again, s plus 2 times. Okay, and that's not so difficult. Okay, these things are infinite. So if at some point I have an I, that means that I is the highest one here, because that is the one on the upper envelope. If at some later point I see j, then j is the highest. So they switch. So there must have been an intersection point. Okay, here I again, I get another intersection point. Okay, so now you have to think, which I'm not going to do, should it be s or s minus 1 or s plus 1 or whatever? But you can see that the number of repetitions relates to how many intersections you have. And actually it turns out that if they intersect s times, then you need to put this s here. Okay.
It's also use the X monotonicity. They're not curving.
This uses the but they are not fully defined. So they have endpoints. Then I claim you get exactly the same thing, except now I have to put a +2. Okay, proof is going to be the same. So, okay, again, we're going to label things. And now, essentially at the beginning and at the end, I can have that here I had J and here I have I, but they don't need to intersect because this one ended. Same thing on the other side, so that's why I get a +2. Okay. Let's very quickly, and then I think that would be a good time to wrap up, look at the much more challenging case of a single cell. Okay, so now I'm no longer, yeah?
Can you repeat what X monotone curve is?
X monotone curve is that intuitively it never curves back. Formally, every vertical line intersects it in only one point. Okay, or if it has endpoints in at most one point.
And what is the notion of complexity for this upper envelopes?
You count. So formally, I would say that the complexity is always, in this case, number of vertices and number of edges. So I have to count maybe formally the 1 for this vertex and then +1 for this edge and then 1 for this. So the total number of features, vertices, and but of course here asymptotically it's good enough to say, okay, how many pieces do I have? How many edges? So 1, 2, 3, 4, 5, 6, and so on. Okay, so I claim that if I have curves that can have endpoints, the complexity of a single cell is this thing here. So it's the same asymptotically as the upper envelope. Okay. By the way, the bound for the upper envelope, that's tight. So there are a collections of curves, each pair of which intersects at most s times, such that you really have this the same bound as for the Davenport sequence.
For every S?
Hmm?
For every S?
For every S, I think. So what is actually quite tricky is if you take S equals 1, okay, then every pair of curves can intersect at most once. So you get ds3, so this n alpha n. So now coming up with a collection of curves that intersect the most once and whose upper envelope has complexity n alpha n, that I think you can get easily if you take the Davenport sequence that has this property and you make curves. But now if I say, okay, you're not allowed to use curves, you should have line segments that are straight. Okay, they also intersect at most once. So you definitely know that it's not worse than n alpha n. But now can you get a collection of straight line segments that sort of implements this Davenport sequence? And that's super difficult. But it can be done. So even for line segments, the bound of n alpha n is tight. Okay, so now for a single cell, obviously it's at least the upper envelope, but because the unbounded cell from above okay, the upper envelope is part of it, so to speak. So the question is, can it be more? And the answer is no, or at least asymptotically it's the same. And yeah, I will just hand wave the proof a little bit. It's not very difficult, but you have to sort of sit down a little bit and verify that everything that I will hand wave now is really kosher. So the first observation is that, okay, if I look at a single cell, there are also these holes inside the cell. And the complexity of this cell is sort of the complexity of the outer boundary plus the complexity of this hole. And maybe there's another hole. But I can just do these things separately. And then add the bounds. So if I take this out, okay, then here I have n minus 3 things. Here I have 3 things. I look at now the outer cell defined by these 3, and I add that complexity to this. And because what I'm adding is already, I mean, it's a super linear function anyway, that's fine. So essentially, it's easy to see that I only have to look at one component of the boundary. So let's forget about this inner thing.
Lambda.
This is well, not shorthand, but similar. This is how people typically write what I used to write as ds s of n is the same as this lambda, or yeah, as opposed to. And so this, if you see a paper with this lambda, then it refers to the length of the Davenport Schinzel sequence. Okay, so I'm looking at one component, and now I simply say that n is the number of things of this component. So you would like to do the following. I simply go around, let's say that the component is the outer boundary of the cell. I walk around that outer boundary. Let's say I start here and I say, oh, I see here for segments, I see segment 1, segment 2, 3, 4, 5, here 6, 5, 6 again, 4, and so on. And then argue that this is some kind of Davenport Schinzel sequence. And then hopefully it's also a Davenport Schinzel sequence of the right, for the right value of S. So there's some indexing missing. So for instance, is it true that if I take S equals 1, right, which I have to do for segments, if I want to get this ds s plus 2, then I cannot have, so that would be ds3, I cannot have ij, ij, I.
You can, once going down. Off by.
Yeah, so something like this where I have 1, 2, 1, 2, 1. Okay, so now you can think 2 things. You can either think, oh, this is simply wrong. The S plus 2 should be S plus 3 for the, maybe a single cell can be more complex than the upper envelope. Or you can think, okay, maybe this was a little bit too easy and it needs to be more delicate, the definition of the sequence. And actually that is the case. So I guess maybe based on what you're saying, you already have one idea how you should modify the sequence.
The intersection is sort of going upwards.
There is something with up and down. I mean, here, okay, I'm getting back to 1, but here I'm sort of below and here I'm above. So I'm going to distinguish between sort of the top and the bottom of something. So you can think about it as each, so now I'm going to curves instead of segments. Each curve, I actually turn it into two curves, sort of for the top and for the bottom. And they get different labels. Right, so now instead of n labels, I now have two n labels. Fine. Okay, so everybody gets duplicated so that this problem that I had one here and then one here again, that doesn't, it's not a problem because now I have one and one prime, which is a different symbol. This still doesn't work. So I will say in a minute what else you need to do. That's a little bit confusing. One thing that you need in the proof, and that has to do with this up and down maybe, is what is called the consistency lemma. And that's the following. Suppose I follow this segment, let's say the bottom side, from one endpoint to the other endpoint. Okay, and I have my single cell, which is the green stuff. And okay, maybe here the red curve contributes to the boundary, and here again, and so on. I could also, instead of following the red curve, I can follow the boundary of my green cell. Okay, so here, this is maybe the single cell here. I follow the boundary of my cell, and I go here, I go here, I encounter the red curve again, I follow the boundary of my green cell, and so on. And this consistency lemma says that these two orderings are the same. So the green curve, so here along the red curve, this is 1, 2, 3. Then along the boundary, I should encounter them in the same order. And so this picture is supposed to illustrate that you cannot, that it cannot be otherwise. So here I'm following green, I have one, and then I encounter this one. And apparently it's not possible that now I encounter this middle one, because that would be in the wrong order. Then I have 1, 3, 2. And yeah, I guess you have to argue more carefully, but what you see here is, okay, if I go back here, okay, I'm looking at the red side. So the question is, can it go like this and then like this? But what you see here is that the cell is on this side, it's to the left. And when I get here, here it's to the right. So that doesn't work, right? Maybe on this side, perhaps, but these two are two different things. So that means that this ordering is consistent. So that is somehow relevant. Then, okay, now I'm going to define the sequence. So first of all, you need to worry about the fact that in this single cell for the outer boundary, this is not a sequence with a start and an end, but it's a circular sequence. Okay, Davenport Schinzel sequence says, okay, from here to here. So somehow you have to start. So you have to pick any kind of edge as the start of the sequence. Then, okay, from here I can now follow, and I get my my sequence. But now you also need to give different labels to things. If I follow this blue arc, I've things that come sort of before the start and after the start, and they also need to be treated differently. So now I have 4 end symbols. And then, okay, the claim is that now it's a Schinzel sequence, and that I have no alternating subsequence. And again, I'm not going to prove it, but just show you what you need to do or need to argue. So we need to show that you don't have this, And what you can argue is that, okay, suppose I have ij, that now essentially sort of here you can charge it to an intersection. So there's an intersection here. Okay, if you have an extra, if s equals 2, okay, maybe you could add something, and but then there would be an intersection here, and that way the total number of alternations is not more than s plus 4. So why is there an intersection? So here you see this picture. I have so I have I, which is red. I follow the boundary. I get J, which is blue. I follow the boundary. I get I, which is red. I follow the boundary. I get J, which is blue. Okay, now I had Ij. And you see that in this picture, the blue curve intersects the red curve. Okay, but that's in this picture. Why would that be the case? So what is maybe for these kind of things, what would you try to use? Something that tells you, oh, if you have this, then you must have an intersection. So what is that? This? It's a K33 or a K5. Okay, in this case, I can point you to a K5 that shows that there's an intersection. So what is our K5? Each of these 4 pieces corresponding to Ij, they become a node. And I put a node in the interior of my cell. So those are my 5 nodes. What are the edges? Well, for instance, I know I have an edge from here to here. I can sit because I follow the boundary of my cell from here to here. Okay, also from here to here. So the edges sort of in consecutive nodes, they're simply embedded as the part of the boundary of the cell. And we know that 2 parts of the boundary of a cell, I mean, these parts are all disjoint, they don't intersect each other. I also have, okay, for this special node here, since it's in the interior of a cell, I can simply route path to everything on the boundary of that cell if I want, and it doesn't intersect. And I also have, so you need to make sure that you have embedded for every pair of things, you found some kind of embedding. And then this embedding is also using actually the curves themselves, right? And because the curves are simple, I know that, okay, they don't intersect among each other, but if you look at it, you will see that the only possibility for an intersection, because the way you've embedded it, is between this, and that means an intersection between the red and the blue curve. So, okay, this is something where you really have to sit down and stare at it and think, are they missing a case here, or is it really true? So, but you have to, the main thing is to specify what exactly are the edges, how are they embedded? Well, you use the boundary of the cell to embed them. For this, you simply use path to these things. And yeah, then you also have this embedding along the red curve, this along the blue curve, and then you verify that all of them, they cannot intersect by the way you've defined them, except for this intersection, which is between the 2 curves. Okay, so I think that was what I wanted to say today. Are there any questions?
Your triplet in high dimension or something.
No, there's nothing like that that corresponds to like surfaces, upper envelope of surfaces in high dimensions. There are, I mean, bounds for single cells and for upper envelopes and so on. They are known also in higher dimensions, but not going through any similar thing like the Schinzel sequences.
Problems here.
There is things called Voronoi theorems which look at the cells of like number of cells generated by half spaces or low degree columns, but not in the upper envelope, but how many cells can you generate? So, sign patterns of
Yeah. So, but I mean, also for upper envelopes, bounds are known. But yeah, they're proven in a different way. And there, many of the bounds are not yet tight, and sometimes even sometimes it's just a small thing like, oh, is the upper envelope in 3D, is it n to the 2 plus epsilon or n squared log n or n squared alpha n or something like that. Probably in even higher dimensions than 3, maybe the gaps are sometimes bigger. You also, what is also interesting is the number of, let's say, trapezoids, or let's say 3-dimensional or high dimensional analogs of these trapezoids. How many are there? Like in 2D, if you know that the arrangement has a certain complexity, and now you do the vertical decomposition, you get the same complexity, right? Because how do you make the vertical decomposition? For each endpoint or each intersection point, you shoot up and down. Okay, and that's it. In 3D, it's more complicated because you're not shooting down from vertices, but you take, let's say, a collection of already 4 planes. Okay, so we have all these planes, they define a subdivision into cells. The number of cells is n cubed. That's easy to show. But now, if you want to decompose this into, let's call it prisms, which, for instance, if you want to construct it using randomized incremental construction, could be useful. So how are these prisms generated? You take an edge of a cell, and then from that edge, you erect a vertical wall. But then if I have a cell, and there's an edge here, and an edge here, this creates a vertical wall going up, this creates a vertical wall going down. So I get an intersection between these 2 walls that you don't see by just looking at the boundary itself. Like locally, it doesn't appear. It appears because of the interaction of the top of the cell and the bottom of the cell. So there's also a lot of work on trying to bound the number of, if you want to cut this arrangement into pieces that are sort of either simplices or these prisms or something like that, how many pieces do you need? And this becomes, especially in higher dimensions, higher than 3, or when these things are curved, this becomes quite difficult. First, solve the other open problems that I mentioned earlier, and then you can come back for more. Yeah, so I'm sure that I don't remember which bounds are still open. I'm sure there are still bounds that are open. It's, yeah, I mean, they're nice problems, but I guess it takes some time to get into this area.
By now, it's the sequence are very well studied.
Therefore, you see the Schinzel sequence, that is sort of closed. complexity of decomposition of, I don't know, surface patches of maximum degree S in 17 dimensions is probably still open if you want to work on it. That's it.
Last part was completely.